I hope you've enjoyed your first day at Build. Ready for another great day here in Seattle. It's a great day to be inside a conference room without windows. It's marvelous. Let me ask you a few questions. Don't you think it's become far too complex to build C++ apps for Windows? Don't you think that build time, especially incremental build, could be much, much faster? Wouldn't it be great if we could simply recompile our code and get substantially better code gen? Don't you think waiting 6 months for another SDK update is way too long in today's market? Hi, my name is Kenny Kerr, and this is Scott Jones. So what is C++ WinRT? Well, the C++ we know, that's the language we know and love, C++ 17 at the moment. But what is the Windows runtime? And there's some confusion around this, so I want to just clear that up right from the start. There are a number of things that the Windows runtime is not. And the Windows runtime is not only for building store apps. It can be used to build console apps, desktop Win32 applications, NT services, even device drivers. The Microsoft Surface line of products today, they use C++ WinRT for implementing their device drivers. So this is clearly not about store apps alone. It's also not a collection of Windows APIs. There are certainly most, if not all, new Windows APIs on Windows are now built with C++ WinRT, but the Windows APIs themselves are not the Windows runtime. It's also not the universal Windows platform. This is the one that people get really hung up on a lot. The Windows runtime, well, the universal Windows platform is a collection of APIs that are available on a broad set of platforms, but that in itself is not the Windows runtime. So what is the Windows runtime? Well, imagine you have two components and they want to communicate across a stable ABI. ABI being the application binary interface. How do they know how to communicate or what method calls to make? That's described in metadata. So there's a WinMD file that describes all the API calls semantically that this component offers for you. And finally, we have a set of language projections. The language projection takes care of interpreting the metadata and resolving it to a canonical ABI format that they can use across the wire or across the vCalls to make that work into a component. And then we have, let's say component A is built in C#, so you'd naturally use .NET as the language projection. And component B might be written in C++, so there you'd use C++ WinRT. This is the Windows runtime. And so we've mentioned nothing about even Windows 10, the UWP, none of those things. There's no store app technology here. This is the essence of the Windows runtime. And just the other day, I managed to get C++ WinRT running on Windows 7. So really, there's nothing here that is specific to Windows 10. Naturally, the APIs that you build in those components might only be available on certain platforms. But this technology is the essence of the Windows runtime, and that's what C++ WinRT is all about. Scott.
Thank you, Kenny. What I'd like to do is take 2 minutes and just do a real quick intro, just to sort of frame things and orient ourselves as to the technology. Some of this might be familiar to a few of you. So thank you, Kenny. So here I am in Visual Studio 2019. And the first thing I want to do as I'm beginning to develop in C++ WinRT is I want to download the Visual Studio extension for C++ WinRT. I can do that easily from the website, the marketplace site. I can also select extensions, manage extensions, and then I can download it by going to online and typing in WinRT. I already have it downloaded here. Once you've downloaded it, there's some great links over here. There's a Getting Started. I really highly suggest you click on that. That's going to take you to a lot of rich documentation that we've been developing over the past year that covers the gamut of all the use of all the entire library, C++ WinRT. Well, let's see what that has delivered, this Visual Studio extension for us. I'm going to create a new project, and I'll type in WinRT. And I have a list of 5 project templates available to me. These are all just a good starting point, depending on the kind of app space that you're working in, whether it's console, a traditional Win32 desktop app, a blank XAML app, a runtime component, that sort of thing. So let's just start very simply with a console application. And I'll select the SDK, that 19H1 SDK. All right, this has created a console app, very simple app. It's got just a real simple source file here that, as you can see, is initializing the WinRT apartment. I think Kenny might have some things to say about that a little bit later. And then it creates a URI object, very object-oriented, and supplies a URI. And then it just simply prints it out. Okay, well, where's the magic? What is the VisX, the Visual Studio extension, done for us? If I right-click on the console application project node and select Manage NuGet Packages, this might be new to some of you, might be review, then I can see that the CPP WinRT NuGet package has been added, a reference to that has been added. And we'll see in a moment what that does for the project. The next thing I'm going to do is open up the properties sheet that is part of that template. And what you see here is a link to, right here on line 7, a link to the NuGet documentation for the project properties. So this gives you a complete listing of all of the project properties that you can set to customize your project. And some folks are accustomed to unloading a project, editing the project file, reloading it. The reason that the property sheet is here is just to make that a little easier. You don't have to do that. You can just add to this property sheet directly. So let's see how that might work. Let's change the verbosity to high, and then I'll go ahead and do a build. And what you see down below in the output window is a verbose spew. You can see that in just 2 seconds, we've created a projection of the entire Windows WinRT API surface. And you can see all of the input parameters and so forth. This is the result of setting verbosity to high. Normally, we wouldn't see this, but just to demonstrate the use of those properties. Let's see what that's done for us under the hood. I'm going to click on Show All Files, and then I'm going to drill down into my intermediate folder, Debug, under Generated Files, under WinRT, and I can see the base library header, and I can see that this was generated by the latest version that was just published yesterday of the NuGet. And then I can see, as I scroll down here, all of the top-level namespace headers that were just produced in 2 seconds for the entire WinRT surface. So it's very, very fast. You have the ability to make use of that technology yourself. If we drill into the Packages node here, we see the result of the NuGet package reference. It's brought in the compiler itself. This is the tool that Kenny and I have developed in the team. And this is what actually marches over all the Windows metadata files that Kenny described and generates those top-level namespace headers for your use. And then if I drill down under Build, Native, then I see the MS Build support files. If you're familiar at all, props and targets and that sort of thing. Then you see a number of properties defined here. Again, those are all publicly documented, so you can use those to customize your build. All right, let's return to the source, and I'm just going to drop a breakpoint in here, and then we'll run it and see what this does. All right, I'm not going to actually run the app. I'm not interested in that so much. I want to draw your attention to the debug visualization in the lower left corner of the screen. As you see, here's my local object URI, and you see the string representation of it. And then you see all the public properties as defined in the metadata presented along with their current value and their type. So this is much like a C# kind of a debugging experience, very, very useful, very user-friendly, and it's nested. You can drill down. If I've got properties that are themselves complex objects that are described with metadata, then I can continue to drill into that. So it really helps with the debugging experience. So you can see real quickly there, again, there's the Visual Studio extension that we started with, and that in turn pulls the NuGet down. The NuGet is also separately available. You don't need the Visual Studio extension. It provides project and item templates and a debug visualizer that we just saw, as well as the NuGet reference, but the NuGet can be added to existing projects to light them up with that build customization. Kenny.
Thank you. That's great. So what I want to do now is look at some of the investments we made in the tooling itself and show you some of the things that will benefit you indirectly just by having upgrading to C++ WinRT 2.0. So the first thing is a C++ WinRT, CPP-WinRT.exe itself has fewer dependencies. So what does that mean? So in version 1, if you run a tool like dumpin/dependence, you'll see a whole long list of dependencies. Now, to be fair, some of these are forwarding DLLs, so they use a technology called API sets. Not a big fan, but these are all built into Windows 10 in theory, and so they shouldn't. You can copy the executable onto any Windows 10 machine, and it works. The trouble is sometimes this doesn't work so well. So our build engineers ran the tool on some very tightly constrained build servers, and they realized that row metadata.dll wasn't present. Now that happened to be a bug in that SKU. That SKU should have included it. But it illustrates the fact that we always strive to have tools, or personally, we always strive to have tools that have few dependencies to make it very easy for you to use those tools anywhere. And so with version 2, incidentally, that row metadata DLL is really the is the implementation of the metadata parser for WinMDs, and that's what we used in version 1. In version 2, we have a brand new metadata reader that the source code of which is included with CPP1RT, so that dependency is now gone. In fact, this is the full list of dependencies for CPP1RT 2.0. And the interesting thing about these 4 DLLs is that they're all available on Windows Vista. So we've gone from something that will only run on a fully loaded Windows 10 machine to actually running on any Windows 7 style build server. You can Xcopy it, it's available, and it works pretty much anywhere. Thanks to the fact that all of this code is now written in pure standard C++ using only standard C++ libraries. Looking at it another way, as I alluded to before, we take a bunch of WinMD files. CPP1RT will parse those WinMD files and generate those namespace headers that Scott demonstrated for us. Previously, it used the row metadata DLL, but now everything is included in a project called xlang, which is an open source project on GitHub, which includes all the source code for CPP1RT. So the entire compiler is now open source and available for you to look around, extend, and contribute to. Another improvement is compile time. So this is something that has always been a challenge for a header-only library like C++1RT. Let's look at the way the traditional ABI headers are generated and included by the Windows SDK. So you can see that the ABI headers, there's one per namespace, but they're very, very large. And these ABI headers are very dumb. So all they include is the vtables, the interfaces that you might have to implement or call directly in order to interact with those APIs. But they provide no support for actually providing an implementation or making those calls very elegantly. It's very low-level code that you'd have to write. Contrast that with C++1RT, where we can generate those headers on demand, and you would generate them on demand, either in your build environment or, as Scott demonstrated, even inside of Visual Studio. And these headers have much, much more value. There's a complete implementation for every interface. You never have to interact with the ABI directly. It's a very simple modern C++ approach to accessing the Windows APIs. You'll also notice that the headers are far more granular. And this is intentional. This allows us to really optimize the build time to include only those dependencies we really need to. And thanks to the new metadata reader we have, we can do incredibly accurate dependency tracking, and thus reducing the amount of code we actually include at compile time. These headers are much, much smaller, but they're far denser. They give you far more value. As an example, a single namespace header, such as this one, composition desktop, will include 32 fewer headers today, thanks to that better dependency tracking, and give you substantially better build time. So a lot of investment in the, really the fit and finish in this release. Another thing to keep in mind, again, this is not something you need to care particularly about, but it's something that we've done for you to make your life better, is that generic types are now generated for you. To help you understand what this means, consider this very simple example. We have an async operation of iVector. So just a bunch of generic types that are provided by the Windows runtime. And the trouble with those types is that with version 1, the metadata reader, the row metadata reader we had, couldn't actually give us enough type information for us to accurately generate those types on the fly. So I ended up handwriting those and sticking them in base.h, the base library for C++1RT. But thanks to our new metadata reader, all you now have to do is include the appropriate namespace header wherever they happen to be generated, and it'll just work for you. So async operation is defined in the Windows Foundations namespace, and iVector is in the collections namespace. The only difference for you is that you need to actually make sure you've included that namespace header. Previously, you could have gotten away without including it, but really you should always include the namespace header for the namespaces that you actually depend on. More efficiency. So if you know anything about me and my history, I'm obsessed with performance and efficiency. So I've always considered making something that is a zero overhead abstraction. So look at this simple example. We have an iStringable interface. It makes a very simple method call to the toString method. So really, this should be as simple and as lean as possible. How can we make this more efficient? Well, it turns out we can. So this is an example of basically the code that was generated for C++1RT 1.0. Now, there's some pointer magic here that I'm just going to hand wave over. James McNellis and I gave a great talk at CPPCon a few years ago where we really drill into this. But for this, for the purpose of this demonstration, I want you to just look at the implementation itself. The philosophy around this was essentially to say, The C++ WinRT language projection is going to generate the code for you in the way that you would naturally write it. So it's not going to add any overhead on its own. You have a local H string. It's going to capture the value, transfer ownership into it, and then it's going to return that value, transfer it back to the caller. Very lean, the way you'd write the code if you had to use the ABI directly. So in that sense, it's true that it compiles away to nothing. But what is better than nothing then? How can we possibly improve on this? Turns out we can. So that H string is really the problem. It's a local type that is non-trivially destructible. If we take that away and replace that with a void star, we suddenly have a trivially destructible local. The impact of that is huge. What it means is that this second line, which is essentially the same, is now efficiently exceptional. The result is that we can now transfer ownership of that local back to the caller so that the caller sees no difference in their code, but we now have the ability to tell the optimizer that this code does not require any cleanup. No unwind information is required by the optimizer to generate for the exception handling, and this produces about 30% smaller code gen on the call side, which is a dramatic improvement for many applications. And I like to call this a negative overhead abstraction, to borrow a term from Gornishinov of coroutine fame, because really now we're doing better than what you'd want to do yourself. If you saw code like this in a code review, you'd question it for sure, because now you're dealing with raw pointers, it's unsafe, it's dangerous. But because we're generating the code for you behind the scenes, your code remains modern C++, it remains reliable and robust, while the code under the hood gets more and more efficient. Another improvement is with noexcept. So could we make it even better than that? So we've taken the idea of noexcept, which we all know from C++, and applying it to the Windows runtime. So consider a simple implementation. Here now we have both an implementation of the iStringable interface, as well as the language projection making that call under the hood. The thing to keep in mind is that the call to the toString function or method is never a direct call. It always goes through the ABI. That's the magic of the language projection. This is not a direct call. And because it's not a direct call, it means that we can optimize the ABI in some really interesting ways. Here, for example, is the implementation side of the ABI that's generated for you. The previous one we saw was the call side. This is now the implementation side. And you can see here, for example, how we're calling up into the implementation. And you can see that this ABI provides all the scaffolding, such as the exception handling, to take care of that ABI boundary for you. So you could conceivably throw an exception in your toString method, and it just works by translating that back into an H result. Now, I really didn't want to have any IDL in this talk, but there's just this one slide, so please forgive me. I just want to make one little point about iStringable. So here we have the typical implementation of how you might define the iStringable interface in IDL. And now what we can do is we can add the noexcept attribute. And this turns out to be pivotal because we have the idea of noexcept in C++, as I mentioned, but we have no way of transferring that knowledge from your C++ code to someone on the other side of the ABI boundary. They don't know that you've marked your method as noexcept. And so in this way, we can actually declare that in the metadata and have tools pick up that knowledge and make use of it. And so that gets baked into the WinMD, and then C++ WinRT itself can then light up extra code gen on your behalf. So the first thing we do is with this implementation ABI, we literally just scrap the catch handler. That goes away. And you're left with a very efficient ABI implementation. There's no more exception handling. And as always, we make sure that the noexcept keyword is on the implementation, such that if you happen to have a bad implementation, a bug in your implementation of any kind, and it happens to throw an exception, we'll still terminate the application according to the C++ standard, and you can very easily diagnose that and fix your implementation. However, if your implementation is non-exceptional, you get the best possible code gen that you could imagine. On the client side, we also light up in a similar way. In this case, we know that the H result is always going to be SOK. It's always going to be successful. So we can ally the exception handling check on the call site. And that's critical because that's where you see all of your code gen benefits and improvements in terms of the code size reduction. So you're literally left with the most efficient call side implementation on the ABI, and there's really no overhead in terms of this ABI call. So many improvements have gone into the tooling itself. There's many more that I haven't covered here, but please take the time to look at the tooling and see how much it's improved over time. Scott.
Let's shift a bit now from the consuming side. The projection exists with two halves. There's the consuming side that Kenny was just outlining, and then there are component authors that make use of a projection that's for producing. The first thing I want to discuss is error-prone construction. This was a problem that we had with CPP WinRT 1.0. Is this line of code safe? It's a trick question. Well, it depends, right? Depends on context. Suppose I'm dealing with a consuming projection like we've just seen. So this is the definition of my class in its projected namespace. Well, it could be safe. It depends on whether it's internal to the component or not. If it's internal, then using that projected constructor is going to attempt a call on row get activation factory. And that is going to fail because we haven't registered this class. And this can happen when we're using local, app local, XAML view models and this sort of thing. We're not interested in registering these for external use. They're for our own internal use. They just need to be described by metadata. So this could be a problem. What about if I'm implementing this? I'm a component implementer and I've got the parallel implementation namespace for the my class type. Is that safe to just create it on the stack like that? It is not. It is not safe. If I create it on the stack, I will have a properly reference counted but stack allocated object. And the moment I return that object out to some caller and the stack memory is freed, I now have a dangling pointer to stack memory, which puts me in a heap of trouble. So that's a problem as well. So the solution to both of these in CPP WinRT 1.0 was that we told folks, you need to keep track. You, the developer, you need to behave. So you keep track of what your internal types are, and you make sure that you use the make function template, which will properly allocate on the heap and return the projected type, as we see with my object. Or if you're using an external type, then other object, then you just use the projected constructor. Well, that's hard to keep track of. So in version 2, we've unified that. We have now safe, unified construction patterns. So it doesn't matter which one of those you use, you're always going to end up with the right behavior. The result of this, the way that we make this work is with a new flag, the -optimize, when we run CPP WinRT. And I'll talk a bit more about why we called it optimize, but one of the things that does is it unifies the constructor pattern. And with the result that we've now eliminated entirely that row get activation factory runtime error. The second thing that we've added is what we call make detection. And so we've now got some machinery under the hood that detects whether you're properly using that make function template or whether you've mistakenly tried to allocate that implementation object on the stack. And the result of that is that we've traded a runtime error for a compile time error. Now you'll end up with a static assertion that says, no, you can't do that. You need to use make. Another thing that we've done, well, returning to the optimize flag, what else does the optimize flag give us? In addition to safe uniform construction, it gives us type erased factories. So the implementation of your classes within the component now does not require full knowledge of that implementation type at the factory site. We've got the generated module.g.cpp, which provides the activation machinery, but that's been type erased. So as long as we're not changing, it's only when we add or remove classes that we need to recompile module.g.cpp. The rest of the time we don't. So this tightens the inner loop. Secondly, we've made it possible to use with the safe unified construction, we can use the internal projection ourselves. So if we've got an internal class and somebody else internal to the component, other code is instantiating it, it can just use the projected headers. It doesn't need direct access to the internal implementation headers, which means we don't have to recompile client code if all we've done is change the implementation. So that too is speeding up that inner loop, trying to compile fewer things. And finally, this optimize flag is enabled for all the project templates that we discussed earlier. A few other things that we've been working on. XAML app metadata processing has been a problem also for that incremental inner loop. The reason why, I'll just sort of sketch this out. Suppose I've got two classes A and B in my project. They're described with IDL files. I compile those to WinMD using the middle-RT tool. Those are then merged, this is a requirement for XAML apps, into a single root namespace metadata file, which we then process with the CPP WinRT executable to generate the implementation templates. The problem with that is that MD merge defeats build dependencies. If I only changed A, it doesn't matter. I have to recompile B and C and all the rest. And so the simple solution to that is that we made the compiler behave, and now what it does is ensure that if the resulting template for a class hasn't changed because the originating IDLE hasn't changed, then we just don't write that. So that speeds things up as well. And then finally, the last optimization that we've added is a library prefix, and this is to help with large-scale component development. If you've got a number of static libraries that are all being used to construct different classes and you're assembling those up into a larger component, then you had to play some tricks with macros redefining row get activation factory entry points and that sort of thing, and now you can just supply a prefix that allows you to easily incorporate those and use composition patterns.
Thank you, Scott. That's great. What I want to do now is go a little bit of a deep dive into the C++ WinRT library itself and show you now some of the things that you can take advantage of directly in your code as we explore the C++ WinRT library. So first up, more like C++, less like COM. This is something that's driven me throughout the design of this project to make you able to write C++ code instead of a lot of very Windows-specific COM code. So I wanted to show this slide. This was the first slide I showed at Build last year. And I just want to point at that first line, in the department. That's so last year. You know, you really want to just focus on the C++ code and not focus so much on all of the mechanics of COM under the hood. The good news is that you can just get rid of that line now. You don't have to think about it, and it'll just work. Now, there will still be an implicit MTA, if you know about apartments, created for you under the hood on demand. And you can still manage your apartments manually if you do wish to do so. But in many cases, you can simply ignore the fact that there is an apartment, and it'll just light up for you with simple standard C++ types that you allocate locally, and you just use them. Another improvement is to do with async timeout. Now, it turns out that implementing timeouts in WinRT can be kind of tricky. And so now we've baked that in for you. Here's an example. So you have an async action. Now, this is a void returning async operation. And you can wait indefinitely for completion using the get function. But sometimes waiting indefinitely is not really practical. And so just like we borrowed the get function from StudFuture, we've now also borrowed the wait_for function from StudFuture as well. You can now use wait_for to wait, let's say, 5 seconds. And then you can check for completion. And then you'll know that we're done. So you have a way of now boxing that wait in a far more practical way. And it makes it very easy to build console apps or any kind of application where you have to actually block and wait for a limited amount of time. And it just makes writing that code far, far simpler. As another example, if you have an async operation, this one will return an actual type, an actual value, and an integer in this case. Here again, we're waiting for completion. And now we can just use the get function to actually get the resulting value. So in that second call, we'll not actually block because it's already completed, and it'll simply return the value for you. Very straightforward programming pattern. If you need a bit more control, you can certainly manage the various states that the wait_for function returns. Either it's completed, in which case you can use get to get the result. It's canceled, and you can get notified of that as well. Typically, the application or the client will cancel an operation, so you typically might not manage the state, but it's there for you if you need it. If an error occurs, you can manage that as well, and you can certainly call the get function if you want to rethrow the error, or you can just ignore it. And finally, the started state means that it's still running. The trick here is that you mustn't wait for it again. With a StudFuture, for example, you can stick it in a loop and just keep waiting. With the WinRT async pattern, its primary or only restriction is that you can only ever wait once. So at this point, you typically just discard the async operation, or you might want to pull it if you really want to see when it finishes, but you cannot wait again. So that's just something to keep in mind. Still a lot of new value in terms of being able to box that wait. Diagnosing direct allocations, this is something that Scott alluded to, and it turns out it was a source of a lot of bugs in terms of people using the language projection incorrectly. So I'm going to just drill into that a little bit more. Here's a simple implementation of an iStringable interface. And here we're doing the right thing. We're calling the make function to allocate the sample implementation on the heap and return back the projected type. But you could also just do this. You could take that implementation type and allocate it on the stack, and it would just work. It compiled and sometimes work at runtime. But that's, as Scott mentioned, that's a really big problem. You're bounding a reference counted object to the stack, which is quickly going to disappear. Another risky approach is to use new. We'd never want to have code, application code or component code, that uses new and pointers directly. Modern C++ is all about value semantics, and you really want to get rid of all of those stars, all of those news and deletes. You should always flag them in your code reviews. So that's also a mistake. Even worse is something like this, and I've seen this quite a few times. Someone takes a reference counted object that is a WinRT or a COM type even, that's intrinsically reference counted, and then wraps it in a shared pointer. This doesn't even make sense. Now we have two different reference counts that are managing the same heap allocated object, and this is going to cause you a whole lot of trouble. And finally, sticking it in a unique pointer, that's probably a bug as well, because now you're having a reference counted object, once again, bound to the lifetime of some local unique pointer. So all of these are troublesome, but in version 1, all of these compiled. It was up to you to know that's a mistake, I should avoid that, flag that in a code review, and so on. Thankfully, with C++ WinRT 2.0, every single one of these is now caught as a compile time error, saving you oodles of time debugging mystical failures at runtime. So this is very important for us in terms of turning any kind of error that you could possibly have in terms of bad usage of code, incorrect code, into a compiler error. Now, C++ WinRT is very famous or popular for its coroutine support. It provides very rich coroutine support, and resume foreground is one of those. Resume background is another. It turned out that resume foreground was just a little bit too clever. Now, let me show you a simple coroutine here. Now, we're going to do some complex work in the background thread using resume background. We'll then switch to the foreground thread and update that text box control. It's a very straightforward code. Now let me show you what the resume foreground function actually looks like under the hood. This is the approach I tend to take for all of those awaitable functions. It actually just returns a local value type or an object, in this case called awaitable. And that awaitable type that is returned has these three critical functions: await ready, await resume, and await suspend. And that's how the C++ compiler stitches together your coroutine with the awaitable expression. But it turns out that this little line here was just a bit too clever. I figured, well, if you're already on the right thread, why switch? Why switch back to another thread? Why not just keep on going? It turns out there are cases in UI processing where you want to actually dequeue and repost essentially the execution so that you can unwind the thread. And that happens to be very, very important in some system level UI work. This is sort of the moral equivalent of send message versus post message, if you're familiar with Win32 style programming. We really want post message semantics. And so that's what we do now. We queue without waiting, and resumption always occurs on a new spin of the thread. Conversely, resume foreground is also now smarter. So we also support the DispatcherQueue. The original resume foreground supported the core dispatcher, which was the original dispatcher that was associated with a single core window. The DispatcherQueue is a far more advanced and far more efficient and far more flexible dispatcher that you can use directly yourself. In this example, I'm using the Windows API to create a dedicated or private queue thread. I can then pass that dispatcher to my coroutine, and that coroutine can use resume foreground and easily manage resumption and suspension on the appropriate thread. More interestingly, though, you can now create a dispatcher queue of your own to be associated with any specific context. In this case, what I'm doing is I'm using this Win32 function, this create dispatcher queue controller, to create a dispatcher queue that is associated with a current SDA thread. And this ends up being the way you build a Win32 application that interops with Windows UI Composition or Windows UI XAML to integrate your existing SDA message pump, from classic Petzold style, with the Windows API stack for UI applications. The nice thing here is that we're boxing up all the Win32 code, which C++ WinRT handles just fine, and we're returning a projected type. So the resulting DispatcherQueue controller is a nice projected type that you can use throughout your application now to interact with that DispatcherQueue. So here's an example of what your typical desktop Win32 application might look like. You might have some abstraction, some window class that manages an hwind, perhaps calling create window ex and so on, hooking up a bunch of message handlers. And then we call that create DispatcherQueue controller function to create that queue on the current thread. We can then pass the DispatcherQueue to a coroutine. It can then suspend and resume as you would expect. And resumption always occurs in the message loop itself. And so you can now see how this naturally fits into your classic Win32 style programming very seamlessly. If we look inside the coroutine, you can see how execution always starts on the calling thread, which is natural. It's just a function call. But resumption will always first queue and then unwind the stack. And then resumption actually occurs on that dispatcher thread in the message queue, in the message loop, in the pump that you've set up for yourself. One of the nice things about resume foreground is that you can also call it with a resumption priority. So you can, the default is normal, you could just leave it alone, but you can also say I want to have it higher or lower, and this makes it very simple to do that. However, if you don't want to set the resumption priority and you're happy with the normal priority, you can just take advantage of the fact that the queue itself is awaitable. And it's just a very convenient shortcut. You can say co-wait queue, and it'll do the suspension and resumption as you would expect. The DispatcherQueue, however, has an interesting feature which allows you to detect queue shutdown. This ends up being really important for, again, very fine-grained control of teardown scenarios where you want to make sure whether the queuing actually occurred or it actually failed. So in this case, we know that you've actually resumed the dispatcher thread. All is good. You can carry on going. Otherwise, you'll know that you're still on the calling thread, and you'll presumably take care of some teardown scenario. So you get the fine-grained control of the DispatcherQueue as well as knowing when that operation actually succeeded. A pretty advanced feature that we've added with 2.0 is deferred destruction. This solves a number of problems with teardown, with shutdown. So imagine a simple implementation again, and in the destructor, it's often too late to do anything interesting. For one thing, the destructor is asynchronous. You cannot actually switch threads, get anything done on another thread. You cannot do anything asynchronous at all. And finally, you cannot reliably query for anything. So what we've done in C++ WinRT 2.0 is introduce the final release function. And what that does is gives you exclusive ownership of the implementation. And within the context of the final release function, you can safely interact with that unique pointer ownership of that implementation object. And if you don't move that somewhere else, it'll be destroyed as you would expect, simply deleting the object and it's gone. The interesting thing about the final release, because you have a unique pointer that holds onto it, you can now do something like move it elsewhere. You can move it to another container, manage that completely independent of the lifetime of the object. You can imagine this, you can think of this as a more deterministic model of garbage collection. Even more interestingly, you can turn final release into a coroutine. So here's my coroutine type. I can now unwind the calling thread. I can switch to the background thread. I can switch to a specific UI thread. That's often a requirement for UI applications. And then we can safely perform any complex teardown within the context as before, but with the added ability to switch the context to anywhere you'd like. So this is a dramatically more powerful way of dealing with teardown than you would have with simply a destructor. Going even deeper, we can look at this idea of doing a query, calling the query interface function within a destructor has traditionally been a very dangerous thing to do. So look at a simple example here. We have a main page from a XAML application. And in the destructor, I want to clear the data context. Seems harmless. But it turns out that data context is actually a property on the framework element base class. So under the hood, the language objection has to query for that interface and then set that property. But querying for anything is dangerous. So how do we defeat this? How do we make this work effectively? If we look inside the implementation of our release function, we'll see that what we're doing is we first check whether there are 0 remaining references. If that's the case, we stabilize the reference count. If you have an electrical engineering background, you might think of this as debouncing. We are making sure that that reference count is stable before we go to that final release step. At this point, we can transfer ownership into the final release handler. And so let's look at an example. Here we have that main page again. In the destructor, we can wait a number of seconds on the thread pool just because we can. We can then safely query the dispatcher, which is a property on the dependency object. We can then release the unique pointer, which will call the destructor. And even in the structure, we can safely query for the framework element base class to set the data context property. So all of these now are reliable calls, which previously were certainly not that reliable. So many, many improvements in the C++ WinRT library, many more that I couldn't cover here, but please take the time to look through the library, look through the documentation, and ask me questions afterwards. We've done a lot of work to make your everyday development a whole lot easier.
So where are we headed? Well, we've been in close contact with the Visual Studio team. In fact, from the inception of this project, we've worked very closely between the Windows team and the Visual Studio team is where our team sits. And we've worked recently with the Visual Studio team, and we've persuaded them that C++ WinRT would be much better as a built-in first-class experience within Visual Studio. So the first thing we want to do is we want to move the debug visualizer that we saw earlier directly into Visual Studio. This will have the advantage that it will support both debug and release builds. It will give us debug visualization of all foundation types. It will support custom types if you have metadata available at debug time. You don't need a PDB. And then finally, it will remove the need for this special hook function, if you're familiar with this, which is what we had to add in order to get the visualization logic to reach back into the target application to retrieve the property values. Secondly, we've worked with the Visual Studio team recently to enhance the XAML design experience. So if you're wanting to write a XAML application with C++ WinRT, we're making steps toward that. We really ultimately want full design surface support, so I can double click on that button and have it launch me directly to the click handler in my C++ source. We already have property editing support today, where if you move down to that pane where you have the list of properties, you can type in the name of a handler and it will generate it. So the generation logic is there, just needs to be wired up to the design surface. The next thing we want to work on is incremental development improvements. Much as what you've already seen this morning, we want to continue to improve that experience so that if I make these little adjustments to my interface, that it doesn't ripple through and cause a complete rebuild of the project. And then we're also working to bring first-class development amenities to C++ WinRT. So light bulb tooltips to tell you what namespace headers to include, what namespace usings, better build diagnostics. It's a common build error if you've used this library at all, that if you omit a namespace header, then you'll end up with an unresolved link error, which is difficult to diagnose. So we're trying to resolve that as well. Really just trying to put more fit and finish to the library. The fast ABI, it's been said that WinRT is just calm with more query interface calls. And there's some truth to that. So what have we done for that? We've developed the fast application binary interface, the fast ABI. Fast ABI attempts to surpass COM and eliminate all QIs across the exclusive interfaces implemented by a type, as well as up and down the composition hierarchy that a type participates in. The only reason we would ever see a QI when you're using the fast ABI support is for compatibility with legacy code that is expecting those older style interfaces. And this is targeted towards performance-intensive applications, UI frameworks, and things like that. As we move forward with the Xlang open source project, we've been working to abstract out the underlying dependencies of the Windows runtime that we have, functions like row get activation factory, into a platform abstraction layer. And we are in process of implementing PALs for other platforms, popular platforms. And so we're really trying to extend the reach and availability of this library to other platforms. The metadata specification is public, and so is the Xlang metadata parsing library. And so we invite you to participate in that. You could imagine creating your own custom metadata parsing tool, such as a linter. And the source for cppwinrt.exe is also available online on our GitHub site. Another thing that we've been looking at recently, prototyping, is a native XAML library for C++. There's rich XAML support historically with Windows Presentation Foundation for C# applications. There's been native support for C++ CX applications. We have not had a ISO C++ XAML story. And so we're looking to invent one, to change that. So native Windows UI apps are cumbersome to write. They typically require interface definition, language definitions, metadata for even the simplest types. Even internal app types like view models require this overhead. And so the goal would be to blow that up, to remove all that overhead and simplify the process, and to be able to bind from your XAML application, say a property value, to be able to bind that directly to any underlying C++ type, even a plain old data struct within any module. So I'd like to shift gears a bit and demonstrate some of the work that we've been doing in that area. So in this application, it's a very simple application. You can see we've got several source files and 2 XAML files. Let's just walk through the project real quick, and then we'll show you it in action. So we have a couple of, in our precompiled header, we have a couple of namespace headers, and then the experimental XAML header that we're pulling in. Moving on to the application, moving up from the bottom, here's the WinMain entry point. The application start static method is being passed a callback that simply makes the app object. Let's move up and see what that looks like. The app object derives from XAML app. This is coming out of the XAML header library that we just saw. The XAML app provides a centralized registry of XAML metadata type information so that the XAML runtime knows where to look to find metadata for properties and types to support binding. Inside of the launched event handler, we make a main page. Moving up, we see that main page in turn derives from the XAML page template, which also comes from the XAML header. And this provides binding support, property change notification, and member metadata information. The main page has markup associated with it, main page XAML. As we move on, let's look at that. We see that that page just simply is instantiating a local control. Let's look at the control. The control, in turn, demo control, derives from XAML user control. It's a XAML user control that, similar to the XAML page, is implementing the custom metadata and property change notifications that are required for binding support. The control itself has markup associated. Let's take a look at that. Control XAML, it's a user control. It nests a stack panel, and ultimately it hosts a text box with a text property that is bound to a counter property. So let's see how that works with this new support. Back in control, we see that the data context is set in the constructor, and then when the loaded event is executed, it executes an update async coroutine. Update async is a fire and forget, so it starts off running and returns immediately without blocking the caller. The first thing it does is does a co-await on 500 milliseconds, which causes a thread pool timer to be initiated, and so we end up executing half a second on a background thread, and then it returns to the foreground thread, to the dispatcher, where we increment a local m_counter variable, and then issue a property change notification so that the XAML binding can detect the update. The only required entries for this XAML user control are the supply of a Windows runtime name for XAML, and the definition of a bind function. This is the heart of the library. This is where it really lights up. The bind method is called once by the XAML runtime, which caches the result. It's looking for metadata. It's looking to resolve a string name of a property to underlying storage or to get set accessor methods. So in this case, we simply check whether the value is counter, and if so, we return a direct reference to underlying storage, m_counter. And the XAML member that's constructed around that reference now holds a reference to the object where it can implement get value and set value calls from the XAML runtime. Let's go ahead and take a look at that at runtime and see the result. As we would expect, we've got a text box control whose text property is bound to this underlying counter, which we have indicated to the XAML runtime is associated with our m_counter, which is incrementing, and we're issuing the property change notification. Now, the real benefit here as a developer, well, I really would love to just focus on control.star, right? my C++ code behind, and my markup. I don't want to mess with it. I don't want to do anything else. So let's see how the inner loop is addressed by this library. I want to add one member variable, a string. So I'm going to add an H string, m_text, that I want to bind to. The only thing that's required now is for me to supply the metadata description. So down here in my bind function, I will add in a check for name equal text, and if so, I will return back my WinRT H string member, m_text. In the corresponding markup, underneath the text box that we already have, I want to create two new text boxes. The first one is a two-way binding. The default is one way. And this two-way binding is going to capture the m_text get value and set value calls and propagate both sets and gets from the underlying storage to the text box, updating the text field. The second control, text box control, is read-only, but it too binds to the same underlying text property. So let's take a look at that and see what that looks like. There's my existing incremented counter. And as I tab off, I pick up the update notification. And so the thing to point out here is what we didn't have to write. It's a bit subtle. The binding is taking care of the property change notification as well. So as I had to add a property change to counter, you didn't see any of that code added for text. It just worked. When I updated the value, the XAML member metadata intercepted that, understood that, and issued the property change notification back to the XAML runtime for me. A couple other points about that bind method that I wanted to just mention. This is the bind method that you see here is built into the type, right? It's just a template specialization. You can create this same specialized behavior for any type, any C++ type. It doesn't have to be something that's implementing some WinRT interface. It doesn't have to be a user control. It could just be a POD struct that you want to serve as a view model in your page. It doesn't have to live in the application. It can come from an external library. In fact, it could even be a projected C++ WinRT type, and as part of the projection, we will generate this XAML scaffolding for you. And then the final point that I would like to make is that there is ongoing work with the C++ Standards Committee to introduce reflection, a reflection facility to the language. When that comes along, much of what you see here would be completely gone. It'll be completely automated, and it will work without any sort of coaching on your behalf. All right, so let's return back to the slides. And at this point, we've wrapped things up, and I just want to show you some slides here, some links here. Really the only one that you need to memorize is the first one, because it's the jumping on point, it's the portal. You can find the rest of the links with the first one. And I invite you to ask any questions if you have any. Please come to the mic if you do, and make sure you speak into it.
Yeah,
Thank you.
Thank you for coming. I'm super excited about that last demo. The fact that you could write an application, he made it look so simple, but there's no IDL there. I'm just really, really excited about finally the C++ developer being able to build a UI application for Windows without all of the overhead that has traditionally been part of that. So I'm very excited about where we're going with this. So love to hear from you. Thank you.
Thank you.
So I had a question. Is there a similar thing for DirectX and what interrupts with Windows?
Yeah, for DirectX, you can continue to do the interop as you can do today. A lot of the abstractions, whether it's Windows UI composition, a XAML control, or a Win32 desktop application like an HWin, you can always do interop with that and get a DXGI swap chain surface that you can render to that. DirectX itself does not yet have any APIs that are based on metadata, so there's nothing for the CPV WinRT tool or any other language projection to consume in order to get the API surface. But that's something I would love to see, but it isn't on the cards at the moment. There's nothing to announce there. Any other questions?
And if you have questions that you want to take one-on-one, we'll spill out into the hall afterwards, and you can grab us.
Yeah, we'll be here as long as you need. Thank you very much.
Thank you.